Okay, good afternoon. We're going to continue with the concept of the stored program concept, the von Neumann processor architecture. We want to make sure we understand this process that a CPU follows: fetch, decode, execute. So by the end of today's lesson, we'll have the same diagram we had last lesson, but, oh gosh, with a little bit less help. We need to try and remember what all the different parts are. This one's important for you gamers. Clock speed is not the most important thing anymore. We want to think about other ways that we can speed up a PC other than just clock speed. Introduce the concept of pipelining and how that can also improve the performance of a CPU. So let's get started with where we left off last time. We saw this diagram. Last time we had a table above it so that we could copy and paste. This time you don't. You've got to label 8 things on this diagram. So if you start with a box, if we remember the upside down underpants, that is the ALU, the arithmetic logic unit. I'm going to make this shape transparent, so no fill, no outline, and the text needs to be black. There we go. Oh, I've got a white line rather than a transparent one, so no outline. There we go. And then you can control and drag for where you want it to be. So there's 3 registers. A register is a very fast, very small piece of storage. Can you remember what they're called? We've got some stuff going in, there's a big clue there, and some stuff coming out, there's a big clue there, and some stuff where we can store 2 different things. See if you can remember what all of these are. So input devices send stuff into the computer, like a mouse or a keyboard. Output device receives stuff out from the computer, like a printer or a display. We've got our general purpose accumulator register. What's a register? It's a piece of memory that stores one value at a time. We've got our arithmetic logic unit, which does arithmetic, like adding and subtracting, and logic, like comparing, and unit because it's just made up of lots of logic gates. RAM stores instructions and data. Instructions is your code, data is your variables. We need to know where the next instruction is. That's what the program counter is for. And we need to know what the current instruction is, like add, subtract, etc. So we store that inside specialist registers. The box outside these is the control unit. Program counter and the instruction register inside the control unit. The control unit controls the rest of the CPU, surprisingly. So you've got a couple of minutes now to try and find a definition of each of these. I would leave pipelining till last because it's the hardest. Please. The clock signal is an electronic signal that alternates between on, 1, suddenly gone black, don't know why. So if there's 2 marks for a clock, we need to know what it is, alternating 1s and 0s, and what it's for. And the word synchronize is important. Think of synchronized swimmers. All of their legs are pointing in the same direction. So if we're synchronizing transistors, they're all operating at exactly the right time. So if you have a CPU that runs at 1 hertz, it can do 1 instruction per second, usually. If you have a gigahertz CPU, remember, kick my granny 2 pieces, horrible violent acronym, but it helps you remember. Giga means we have to multiply by 1,000 and 1,000 to go from kilo, mega, and giga. So it's a billion instructions per second. It's not strictly true. It means you can fetch a billion times, and you'd have to decode a billion times, and you'd have to execute a billion times if you wanted to have, and you'd need a frequency of 3 gigahertz in order to do that. because you'd have to fetch and then decode and then execute. Each of fetch, decode, and execute takes 1 clock tick. Unless you do pipelining, and we'll come back to pipelining afterwards. Okay, so we're going to talk through what actually happens. When you switch on your CPU, all of the registers are set to 0, so it knows the program counter is a 0. The program counter points to the address of the next instruction. So that means we are going to, at 0 time, that means time you switch on the computer, it's going to fetch instruction 0. After 1 clock tick, what does that mean? It means the clock goes low to 0 and then back high again to 1, 3.3 volts, logic 1. We are going to decode instruction 0. After 2 clock ticks, we can now execute instruction 0. So it took 3 clock ticks from the beginning of 0, the end of 2, before we can actually execute this first instruction. After that, we can go back round and fetch the next instruction. But it's not instruction 0 anymore, it's instruction 1. Oops. This is the 3rd clock tick, the 4th clock tick, the 5th clock tick. And it just goes round and round and round forever and ever and ever. Or until the CPU pauses, sleeps, or you switch it off. So that's normal execution. 3 clock ticks per instruction. If you've got a 3 Hertz CPU, you're going to be able to execute 1 instruction per second. You've got to fetch, then decode, then execute. Okay, I'm going to share this screen with you in a moment. In fact, you can type it out yourself. tanks.withcode.uk. We'll start by doing a sequence of instructions manually. Nice and easy. You've got a tank. You have to get through all of these waypoints, picking up some fuel on the way, and sometimes shooting some stuff. So we've talked about sequence selection and iteration. Sequence just means we can follow a sequence of instructions. I want to move forwards 1, 2, 3, 4, 4 times. 1, 2, 3, 4. And my tank follows my manual instructions. Nice. I'm going to turn left once and move forwards 4 times. You get the idea. Turn, move forwards. So manually programming the tank is dead easy. I hope we can all do that. The next level, this time there's no manual controller. We have a little man computer. Remember the little man computer? We saw Peter Higginson's little man computer. This one last time, if you remember that, with our program counter, instruction register, and accumulator. So this time on level 2, we have some instructions. So this time for level 2, if you click on the tank, you've got some instructions code here. So let's see what's happening. We have some input devices, like user input and blah, blah, blah. We're going to ignore those for now. We have some output devices, and we, rather than just displaying some text like out, if we submit that and run it, whatever is in the accumulator is going to go to the output here. We've got a 0 in the accumulator, so we're kind of hoping that a 0 will go to the output device. There it goes. Not very exciting. This time, we can still do user output, but we can move the tank. So we're going to tell, we've got some code here. Let's copy and paste all of that into here. What does this mean? We're sending a value into the output device 1. Output device 1 is to move. Which value are we sending? Well, we're sending a value in the accumulator. And we need a 0 in the accumulator. In order to guarantee we have a 0 in the accumulator, we've just made a variable called forwards. So here we've got some data with the value 0 in. I can put whatever I like in here, and that means the data value 56 is now stored here, but that's not going to move it forwards. I need it to say 0. Right. Let's step through. We've fetched the first instruction 503. Where's that come from? Well, 503 is LDA forwards. Why? 5 is LDA, load. 5 something something means load. So what's the 03? Well, 03 is the address of the value. Look, forwards is at location 3. So the CPU says, fetch a value from memory location 3. Okay, so we've fetched a value. What does that mean? It means the instruction register currently stores the value from the first memory location. After fetch comes decode. So we're going to decode 503, and 503 means load the value at address 3. That's what LDA 3 means. After decode comes execute. So what we're hoping is the value at location 3 is going to go into the accumulator. That 0 is already there actually, but it's definitely going to be there. One other thing changed, I don't know if you saw it, but the program counter increased. Because next time round, the next instruction, we want instruction 1. Okay. So when we fetch the next instruction, let's see, we've fetched 912 into the instruction register. If we decode it, we can find out what 912 means, and it means 9 something 2 is output. Output to device 1, which for us is movement. Then we can, we've fetched, we've decoded, we can execute. And hopefully our tank will have moved. Don't know if you saw it. Let's just go a little bit faster. Let's choose a level, level 1. Come on. What's going on? Choose level 1. Oh, that's better. And this time, if we run it, it's only going to move forwards twice. If I want it to go a little bit further, I can just send the value in the accumulator to the output device again, and send the value in the accumulator to the address again. Let's reset the level, restart the level. Oh, now I never understand this. Click yes to reset the code. Now I don't want to reset the code in the tank. Better. So I've still got my code here. I hope that this will move forward to the checkpoint. Done. Okay, so lots of explanation from me, but all you've got to do is actually really simple. Send the instruction 4 times instead of 2 times, and you can collect the checkpoint. I'm going to give you your screens back. The next challenge is a little bit harder. So for level 2, let's have a look. We haven't got any code in here already. What do we want to do? I'm going to put some comments in. I want to fire. I want to aim east, and I want to fire again. And then I want to aim south, and then I want to fire again. Obviously, the comments don't do anything. They're just there for your benefit. So how do we fire? Let's see. Output device 4 is weapons. If we have a 0 in the accumulator, it's going to shoot. So how do we do that? I'm going to copy this and see what it does. First of all, we need to know a memory location with a 0 so that we can load it into the accumulator. I'm going to put all of my data down here. Remember, a von Neumann processor architecture can have instructions, these are instructions, and can have data. DAT stands for data. We don't actually need to have fire. You can specify, I want to load directly from memory location 3, but it kind of makes your code easier to understand if you replace the actual memory locations with a name. That is literally what a variable is. A variable is a named memory location. It's just a space in memory where you can find something. So we're going to send a 0 to output device 4. I only want to halt at the end, and it's important to halt, otherwise we're going to try and execute data, and that's how viruses work. Accidentally tricking your CPU into executing data, most viruses work that way. We don't want to do that. So instead, we want to aim east. How? Well, let's steer the tank. How do we steer? We want to steer east. Oh, this time we need a 2 in the accumulator. So sadly, I can't just do load the value 2. It'd be nice if you could. At A level, we talk about addressing modes. And we want to literally put the value 2 into the accumulator, but this tank doesn't support that. This means load the value at location 2, which is actually 502. So that's not what we want. Instead, we have to make a variable called east and store the value 2 somewhere else at actual memory location 5 or wherever. It doesn't really matter where it is because we've called it east. What do we do with that value? Once it's in the accumulator, we send it to output device 2. And then we can fire. And then we can aim south. Well, how do we aim south? Let's see. We need a value 4 in the accumulator. So we want some data. Storing the value 4. We've just made a variable called south, which is memory location 9 at the moment. But that will change as we add more instructions above it. We load that value in to the accumulator. We send that value out to, what am I doing? Aiming. Yeah, to output device 2. And then we fire. So it's not nearly as easy as Python, where you could just say aim east, shoot. But it's relatively straightforward. So we've got a very limited number of instructions, but those instructions give you complete control over everything that the tank can do. That is low-level programming. Your CPU is fetching, decoding, and executing instructions. I'm going to stop there. I don't think I'm aiming west, but let's see if it works. We press run. It should shoot, aim, shoot, aim, shoot, aim, and then stop. So your job is to adapt this so that it also aims west and then shoots. Please make sure that you save your Word document, close it, and then submit it onto Half Term 3 Computers 1. Thank you for your hard work today. It's not been an easy one to understand, but the important thing is that the CPU works by fetching, decoding, and executing repeatedly, repeatedly, repeatedly. That's all the CPU does.